Hello, I'm Yehan Liu. Welcome to my Lab 4 report about oscillations. The purpose of the lab was to observe and analyze the behavior of a spring mass system moving in 2 dimensions. We used video analysis to collect real-world data and then compared it to a computational model simulating the same motion. Through this comparison, we explored fundamental concepts such as Hooke's law, which states that the spring force is proportional to the displacement from its relaxed position, and the conservation of energy, where the total energy, including kinetic, gravitational potential, and spring potential energies, remains constant throughout the oscillation. In the lab, we rely on several key equations to describe and predict the motion of the spring mass system. In addition to the first 3 equations we have been using, the spring force equation describes the restoring force, and the energy equation is used to calculate the kinetic, gravitational, and spring potential energies at different points during motion. The lab utilized 2 models. The experimental model involved capturing the motion of a mass using video analysis software called Tracker, which provided data on the mass position and velocity over time. And the computational model, created using GlowScript, simulated the spring mass system based on the same initial conditions as the experimental model. This allowed for direct comparison between the real-world observations and the simulation results. And here is a preview of the result. The model and the experiment display similar periodic motion, but the model has slightly higher peaks and leads the experiment, showing a small phase shift. In the experimental setup, the system was defined as a spring mass with air resistance and gravity acting as the surroundings. The system mass was 0.402 kilograms, and the initial position and velocity were obtained from video analysis using Tracker. And the assumptions we made here is that air resistance and friction are negligible. Based on the data extracted from the tracker, we then calculated the spring stiffness and the relaxed length, which were ready to be used as data for the initial state of the GlowScript model. Then here is the code of the computational model, which was created using GlowScript, where I programmed the spring mass motion using the same initial conditions observed in the experimental data. The code included position, velocity, and energy update formulas to simulate the spring's behavior at each time step. This model provided a continuous, idealized representation of the motion, allowing us to predict how the system should behave under the same conditions. These pictures are the output of the code. Then let's see the results. So both the model and the experiment demonstrated periodic motion with similar shapes and frequencies, aligning well over the entire duration of observation. However, the model's peaks were consistently higher than those of the experiment, particularly in the x direction, and the experiment data seemed to lag behind the model, indicating a small phase shift. This difference can be due to simplifications in the model or errors in experimental measurements. There are several potential sources of error that could affect the results. First, calibration errors in the tracker software might have caused inaccuracies in position and data extraction. Second, motion toward or away from the camera could have introduced perspective distortion, inflecting 2D tracking accuracy. Lastly, environmental factors like minor air currents could have influenced the spring mass system's behavior, creating differences between the experimental and simulated results. Then let's see the 2 follow-up questions. First one, for your model system, is the energy principle satisfied? My answer is yes. The energy principle is satisfied. According to the picture, the total energy stays nearly constant over time, while changes in kinetic, gravitational potential, and spring potential energy balance each other. This shows that energy is conserved in the system. Then the second question, using the data I obtained in Tracker, make 2 separate estimates of oscillation periods, then compare the 2 estimates and discuss. My answer is, using the data obtained from Tracker, I calculated the oscillation period separately for the x and y direction. The period for the x direction was slightly longer than that for the y direction, resulting in different spring constants for each direction. This indicates that measuring different direction can produce variations in the period, affecting the spring constant and the shape of the resulting graphs. Thank you for listening.